Hi friends, welcome to the channel. So from today, I'll be doing a series of videos called the Concept Through Question series or the CTQ series, where we'll look at a question from previous year question paper. First we see the question, then we look into the concept behind the question. We understand the concepts that are needed to solve this particular question and then come back to the question and solve it. So here let's look at the first CTQ question, which is from the UV visible spectroscopy, and we'll be studying the effects of solvent polarity on electronic transitions. So the question says that in UV visible spectrum of an alpha beta unsaturated carbonyl compound with increase in solvent polarity, which of the four options is the right one? Whether the N to pi star transitions are undergoing a hypsochromic shift and pi to pi star transitions are undergoing bathochromic shift, or is it the reverse of it, or is it that both the transitions are bathochromic shift or both transitions undergo hypsochromic shift? So to do this question, we should have an idea about UV visible spectrum, especially the various transitions involved, the various shifts that are involved, and the effect of solvent polarity on these shifts or transitions. So let's move to the concept behind this question. So UV visible spectroscopy, it's an absorption spectroscopy which is based on the principle of absorption of light. So now let us consider the case of two states. We are having two energy states. The first state that I have here is my ground state, and on top I have my excited state. These are the two energy levels that I'm having, and I have two electrons in the ground state, which is a stable state. Now I irradiate these electrons with some amount of energy, and as a result of the radiation, the electron gets excited to the higher level. But the higher level being unstable, the electron would return back to the ground state, and as it returns back, it would emit radiations. So this is what happens in any absorption spectroscopy. And in UV visible spectroscopy, what happens is that the energy difference between the two states, that is the ground state and my excited state, would have some energy difference, and the electron would absorb energy equivalent to this energy difference, and that energy difference would be in the range of 190 nanometer to 800 nanometer, which is in the UV visible region of electromagnetic spectrum. So the energy absorbed by the electron would be in the region of UV visible range, 190 nanometer to 800 nanometer. And as it absorbs energy and comes back, returns, the energy absorbed and the energy given out, the wavelength or the color of the light that is absorbed and the light that is given out would be complementary. That is why we see complementary colors. Okay. Now, like we have other spectroscopies also. We have rotational spectroscopy, vibrational spectroscopy. Like in rotational, the transitions are taking place from the rotational levels. In vibrational spectroscopy, transitions takes place from the vibrational levels. And in UV visible spectroscopy or the electronic spectroscopy, transitions take place from the electronic levels. So what are those electronic levels and what are those transitions? So the various energy levels or electronic energy levels are the sigma, pi, n, pi star and sigma star, where sigma and pi are the bonding energy levels. N is the non-bonding energy level, pi star is the anti-bonding energy level, and sigma star is also the anti-bonding energy levels. Now sigma and sigma star are due to the presence of sigma bonds. Pi and pi star are due to the presence of pi bonds in a compound or a molecule, and N, non-bonding orbital, is due to the presence of free electrons on my groups, like the atoms in the group that I have would have free electrons. Now the first three that I have, sigma, pi and n, are the, I can call them to be the occupied energy levels, and the last two, pi star and sigma star, are my unoccupied energy levels. Occupied means electrons in their normal state, ground state. Electrons would be found in the sigma, pi and n orbitals. And when I excite these electrons by providing an energy, they get excited to the unoccupied orbitals, which is the pi star and the sigma star. So I can say that in electronic transitions, my transitions are from HOMO to LUMO. That is, my transitions are occurring from HOMO to LUMO, which is highest occupied molecular orbital to the lowest unoccupied molecular orbitals. Now, what are the possible transitions? From my sigma orbital, I can have two types of transitions. One is the sigma to sigma star transition and sigma to pi star transition. Then from the pi orbital, I can have pi to pi star transition. And from the non-bonding orbital, if I'm having electrons in my non-bonding orbital, or if my non-bonding orbital is my highest occupied molecular orbital, then the transitions can be, upon irradiation, my transitions can be N to pi star and N to sigma star. So these are the various electronic energy levels and the electronic transitions that are possible. Clear? So let's look at what are chromophores. Chromophores in UV visible spectroscopy are those groups that undergo the absorption of light. They exhibit absorption of light or radiations, electromagnetic radiations. Those groups are basic units which can absorb the electromagnetic radiations in the UV visible region. Such groups are the chromophores. Now we have different energy levels, like we had the sigma to sigma to pi star, n to sigma star and n to pi star were the various transitions. And each of these transitions would be given by a particular chromophore. A chromophore group would cause each of the transitions. If we have simple alkanes, like the case of a methane, or any other ethane, there would be carbon to carbon bonds and carbon to hydrogen bonds, which are the sigma bonds. And these sigma bonds or the saturated compounds would give rise to sigma star transitions. Now, in the case of carbonyl compounds, I have carbonyl. Next is the case of a carbonyl compound like C double bond O, where I have sigma bonds and pi bonds. So, such compounds have the ability to undergo sigma to pi star transitions. Now, if I consider similar to this carbonyl compounds, there are another set of compounds like my alkenes or the alkynes also. They also have sigma bonds and pi bonds similar to the carbonyl compounds. And due to the presence of pi bonds, such groups can undergo unsaturated compounds can undergo pi to pi star transitions. Then we have certain chromophore compounds which have oxygen or nitrogen, sulfur and other halogen containing compounds. Such atoms are present in the compound. Those compounds, like because of the presence of oxygen, nitrogen and or lone pairs or free electrons would be present on the atoms, and these free electrons would be present in the non-bonding orbital and they can undergo transitions giving rise to N to sigma star transitions, like the case of, so here I can take the case of like CH3OH if I take. So what happens? This oxygen would have free electrons or the lone pairs that undergoes transition from the non-bonding orbital to the sigma star orbital. Then we have the carbonyl compounds which can undergo transitions again from the non-bonding orbital to the pi star. Because if you look at the carbonyl compounds, it is C double bond O, where the oxygen also has lone pairs of electrons. Free electrons of the oxygen of carbonyl compound can also undergo transition to the pi star orbital from the non-bonding orbital, giving rise to the N to pi star transition. So these groups that cause the various transitions are the chromophores, and these groups, each of the group would cause the transition at a particular wavelength. So the absorbance, it would absorb light at a maximum wavelength. A maximum absorbance would be given at a particular characteristic wavelength. Like if you have the case of alkenes, this value would be around, for alkenes, if I consider, my absorbance would be around 170 nanometer. It would be around 175 nanometer. And for alkynes, if I take, my value would be around 170 nanometer. So similarly, each of it, carbonyl compounds would give from some 200 to 220, the transition, like whether sigma to sigma star, N to sigma star, each of the transition which would occur at a characteristic wavelength. Okay. Now what we see here is a graph or the spectrum for a UV visible spectra that we see here. UV visible spectroscopy would give a spectra between absorbance and wavelength. Okay, now we get the parabolas like this, the curves we get, and my substance would absorb light at the maximum absorbance would be at a particular wavelength, which is the lambda max. Now, if along with the chromophore, if I have some substituents, replacing some of the hydrogens in the chromophores, if I put some substituents to it, like OH or NH2 or any other group, substitutions I'm bringing in to my chromophore means those substituents has the ability to alter my wavelength and absorbance. My lambda max value and the absorbance value can be altered by the addition of some substituent groups to my chromophores. And now let's see how the wavelength varies. Sometimes there are certain groups when I add, they can cause the wavelength to change to a longer wavelength side or to a shorter wavelength side. Now, if my substituent changes the wavelength, has the ability to change the wavelength to a shorter wavelength side, if it shifts the lambda max to a shorter wavelength side, then it's called a blue shift. And if my wavelength is shifted to the longer wavelength side, then that's called a red shift. And the blue shift is also known by another name, which is blue shift is the hypsochromic shift. It's the hypsochromic shift. And my red shift is also called the bathochromic shift. Another name is the bathochromic shift. So these are the two other names that if my group substituent can cause a shift in the wavelength towards the left or the right, I can get hypsochromic or blue shift and bathochromic or red shift. Now, the substituent, certain substituent has the ability to alter the absorbance also. It can increase or decrease the absorbance or the intensity of absorbance. So such groups can cause two types of shifts. One is the hyperchromic shift and the next one is the hypochromic shift. If my substituent can bring about an increase in the intensity of absorbance, then it's a hyperchromic shift. And if my substituent can cause a decrease in the absorbance intensity, then it is a hypochromic shift. And those substances, those substituent groups that can increase the intensity of absorbance, such groups are generally called the oxochromes. Oxochromes, we call them the oxochromes, and those are groups like our OH group or NH2 group or Cl group. So such groups have the capability of changing the intensity of absorbance to a higher value, that is hyperchromic shift. Clear? These are the various shifts we have. Now let's look at how the solvent, the polarity, if I'm adding a polar solvent, then how would these shifts, which of the following shifts, how would the transitions undergo any particular shift? Now solvents that I have, the solvents can be of two types. They can either be polar solvents or they can be non-polar solvents. These are the two possibilities. Polar solvents mean I can have like water or my alcohols. These are my polar solvents. Non-polar solvents means like hexane would be an example of a non-polar solvent. Okay, right. Now, what happens to my transitions when I'm having polar solvents? Polar solvents would interact with polar solutes. My solute particles, if they are polar, then that has the ability to interact with the polar solvents via some dipole-dipole interactions or like hydrogen bonds or any other dipole-dipole interaction. Forces between them can happen. If I consider sigma to sigma transitions, if I'm considering the sigma to sigma star transitions, in such transitions, it is in saturated compounds like the case of an alkane. So like if I have CH3, CH3, now my such compounds are not polar, they are non-polar compounds. Non-polar compounds are not affected by the polarity of the solvent. But if I have certain other polar compounds like as CH3, CHO, CH3, CHO aldehyde groups like so where I have a carbonyl group, so where CH3, CHO would be a polar molecule. So such compounds can give rise, can interact with the polarity, the solvent polarity. So first let us consider how the N to pi star transition would vary with the increase in the solvent polarity. So this is the normal case where we are having N to pi star transition. Now I'm increasing the polarity of the solvent. I'm adding a polar solvent to it. The polarity of the solvent increases means what happens? Now here I'm having my carbonyl group like this, C double bond O, and the oxygen would have unpaired electrons. Now to this I add my water molecule, which is a polar solvent. Water means it would be HOH. This would be the case. Now between this oxygen and the hydrogen, there is possibility of hydrogen bonds. This has the possibility for hydrogen bonds. And as a result of hydrogen bonds, what happens is stabilization occurs. We get stabilization of the compound, or the molecule gets stabilized. And what happens when it is stabilized? Because I have carbonyl group which is polar, I have my water molecule, the solvent, which is polar. These polar molecules, they interact each other, they form hydrogen bonds. As a result of hydrogen bonds, stabilization occurs, and as a result of stabilization, energy would decrease. Stable means lower energy. So my N, my non-bonding orbital, would now be in a lower energy state, and it would be lower. But my pi star, it is in the same state. My N is the one which is interacting. My non-bonding electrons are interacting. That causes the stabilization of the molecule. As a result, my non-bonding orbitals becomes lower in energy. As a result, you can see that the overall energy difference between N and pi star increases. The energy gap that I have here, this energy gap delta E has increased, which means that as energy, we know that E equal to hc by lambda. So as my energy increases, my lambda value decreases. If the lambda decreases, we saw that lambda is shifting to a shorter wavelength, means this is a blue shift. And a blue shift is also known as hypsochromic shift. This is a hypsochromic shift. That is what happens in N to pi star transition. With the increase in solvent polarity, we get a blue shift. Next, we have the case of pi to pi star transitions. I'm moving from pi orbital, pi energy level to the pi star energy level. Now, in such cases, we know that we have this C double bond C. This is alkenes are a case where they show this pi to pi star transition. Now here as such, in the normal state, in the ground state, pi energy level, now this is neutral. The electrons are equally shared. But once it undergoes the transitions, these pi electrons would undergo a shift to the pi star orbital. And that's how we get the pi star orbitals to become polar. In the ground state, in the pi state, energy state, it is less polar, it's not polar. But when we have the transition from to the pi star, the electrons are traveling to the pi star orbital. So as a result, as the pi bonds are shifted, a transition is occurring of the electrons are shifted. So in that case, the pi star orbital, my anti-bonding orbital, becomes more polar. So whichever is more polar, that orbital or that energy level can interact with my polar solvent via some interactions, but some dipole-dipole interactions can occur. Here in this case, my excited state is more polar. In pi to pi star transition molecules, my excited state is more polar, and such molecules would show pi to would cause some bond of some sort of dipole-dipole interactions in the pi star antibonding or the excited state, and as a result, the pi star orbital, because of this stabilization, because of the dipole-dipole moment interaction, dipole-dipole interactions, this pi star orbital becomes stabilized and it is decreased in energy. Pi star gets lowered, and but the pi orbitals remain in the same place. So we can see that here I can see my overall delta E is decreasing. So if energy decreases, my lambda would increase, and this would give rise to, as lambda increases, this is the red shift that I have. Red shift is also called a bathochromic shift that I have. This is, I'm having a bathochromic shift when it is a pi to pi star transition, whereas I'm having a hypsochromic or blue shift when it is N to pi star transition. So always remember, B and B does not come together. That is, blue and bathochromic won't come together. Blue is for hypsochromic and red is for bathochromic. Understood. Now let's move to the question. Let us apply the concept to this question, our first CTQ question. So here they've considered the alpha beta unsaturated carbonyl compound, and they're asking for what would happen to the N to pi star and the pi to pi star transitions with the increase in solvent polarity. So we saw that for carbonyl compounds with the increase in solvent polarity, N to pi star transitions undergo hypsochromic shift or the blue shift, and pi to pi star transitions undergo the bathochromic shift. So I can say here in this question my option A is the right option. So that's it for today. Hope you enjoyed the CTQ question number 1. See you again with another video. Thank you so much.